In this video, we are going to discuss this phenomenon, which is known as quantum tunneling. Consider a ball and an inclined plane as a barrier to the path of the ball. Now assume the ball have to cross this inclined plane. So for that, we have to apply some amount of energy to the ball. If the energy is insufficient, the ball will not be able to cross the kinetic energy greater than the potential energy of the ball, which it will attain at maximum point of the inclined plane, that is mgh. Now the ball easily crossed the barrier, losing some of its energy. Now take the same type of example at quantum scale. Consider an electron which can only move along one axis, like we have taken in our previous video on Schrödinger equation, and assume that there is a barrier in the path of electron, let's say due to the electrostatic potential of another electron. So due to this electrostatic repulsion of the other electron, there is a region of space where the influence is felt by first electron while passing it. When first electron try to cross this region, the second electron energy is less than V0, it will bounce back and remains on the left hand side of the barrier. And when energy of the electron is sufficient larger, that is E greater than V, it can be anywhere, and while crossing the potential barrier, the speed of the electron decreases due to the loss of energy. So this is all classical, no excited thing till now. But when electron have less energy than the potential barrier V0, even then it has chances of crossing the barrier. So here comes the interesting thing, which can be explained quantum mechanically. Let's first simplify our potential barrier. Just for the sake of explanation, consider it of rectangular form. Now we will use Schrödinger equation to analyze the problem. We have two cases, energy greater than V0 and second, energy less than V0. Case 1, when energy is greater than V0. It is not interesting as it is all classical, and solution to this case is like this. And probability density function for this case look like this. Electron can be anywhere in this case. Now name it as 1, 2 and 3, which have different potential value. Now on doing calculation by using Schrödinger equation, we can find the wave function. But let's don't go mathematical in this video. I will make a different video on that in future. But if you are curious how we will calculate the wave function, you can see my video on finite 1D potential valve for reference. It has almost same type of calculation. So on doing calculation using Schrödinger equation, we get wave function of this form in the three regions. In region 1, we have terms corresponding to the transmitted wave. In expression of transmission coefficient and reflection coefficient, we see that they also depend on the width of the potential barrier. So quantum tunneling also depends upon the width of the potential barrier, which is given by this expression. Don't care about this expression for now. This is all mathematical. So now we have understood what is quantum tunneling. Quantum tunneling is used in tunnel diode, quantum computing, and scanning tunneling microscope. So that's all for this video. If you have watched this video till here, don't forget to subscribe to the channel. See you guys in the next video.